We will start off with Craig Hartman presenting today, and then we'll move to the video portion with Barry Christensen. We'll go ahead and toss it over to Craig to start.
All right, thank you. Welcome everyone back. This is the third in our series of 4. And as you know, we're offering 4 hours, 4 professional development hours, or 0.4 CEUs, because the CEU is 10 hours. And you can get that by emailing to the same emails that you get from invitations and so on to Tyler. We are going to review just a few slides today. They will look familiar if you were in our last seminar, but we're going to talk about them from a very different point of view, from the point of view of startup maintenance and troubleshooting. So the first slide shows our AC to DC converter. And the AC to DC converter is composed of 6 diodes. I refer to them as check valves a lot of times. If you're not an electrical person, that's what they are. They just let the current flow in one direction. Now notice on this that if you put your meter between the positive bus, that would be the line on the top, the positive bus, and sometimes that's labeled P for positive, sometimes it's labeled plus for positive, whatever it is. You put your red meter there, and you put your red lead, and then you put your black lead on A. You are essentially measuring across the diode. And because the current's trying to go backwards, you should not see continuity. Now, if you simply switch your leads and put the red lead on A and the black lead on positive, then you should see continuity because now the current's trying to go through in the correct direction. So with 2 very simple measurements on the drive with a standard volt-ohm meter, you have tested that diode. You do the same thing between P and B and P and C, and then you do the same thing between A and N, B and N, C and N. You've got 12 simple tests there. And if you get continuity where you shouldn't, then you have a shorted diode. If you have no continuity where you should, you have an open diode. So this is a fairly quick test. Barry tells me this is one of the first things he does after he gets the drive open. And I'll talk about him in a moment. We're very happy to have Barry here. Barry is a long time drives person who has designed and built and troubleshooted, and he repairs drives and everything. So let's go to the next slide. And the next slide shows our capacitor. So we call that the DC bus. You've got ripple from the AC to DC converter. You have to get rid of that ripple. And so you put the capacitor on the DC bus, and you notice in the diagrams at the bottom, now we're getting rid of that ripple and we have a nice positive DC. So here between P and N, or plus and negative, you have access to that capacitor, and that is an electrolytic capacitor. You can test that capacitor if a drive has not been used for more than, let's say, maybe a year or so. Most manufacturers will recommend that you reform that capacitor, and that includes application of lower than rated voltage in order to bring that up to speed. We won't get into that in detail this time, and different manufacturers have different recommendations. If the drive is running, then if you measure from the positive to the negative bus with your meter in AC mode rather than DC, you should see a very low ripple, say less than 3 volts in a properly functioning drive. The next slide is going to bring in our inverter. Oh, I'm sorry, I got one slide ahead of myself. This is the soft charge circuit. So soft charge circuits can vary somewhat, but this particular one has a resistor and a contactor. When you first energize the drive, if you don't have that in there, it will basically be a short circuit between the power system and that capacitor. Electrolytic capacitors don't like that. They tend to blow up, and we tend to think that VFD blowing up is a bad thing. And so all manufacturers that I know of low voltage drives include a pre-charge or a soft charge circuit. So when you first energize the drive, the capacitor fills through that resistor, which limits the amount of current going into that capacitor. It also prevents fuses from blowing and breakers from tripping and so on. Now, once the voltage on the capacitor is at your rated voltage, then the contactor will close. It bypasses that resistor, and so that resistor is in there for a fraction of a second, and then it's gone. So we're going to take it out of the circuit because it effectively isn't there once that contactor closes. As you can probably see, if you energize the drive and then you measure the DC bus and there's no voltage on the DC bus, there's a very good possibility that that resistor is broken. Let's go to the next slide. Now this slide shows the inverter. Now we're going from DC to AC. And I'm showing 6 switches. Of course, in a real drive, as we talked about before, these would be IGBTs. But that's all an IGBT is functionally in the drive. It is a switch. It turns on and off to create the output waveform. Now, if you have your standard voltometer, you can measure between P, the positive bus, and that top motor lead, and you can test that one IGBT. You test it exactly the same as you do the diodes. And so with 12 tests, you can test each one of the IGBTs, see if that IGBT is open or shorted. Let's go to the next slide. And this slide shows a PWM output. So you can see that the dark blue is your voltage and the magenta is your current. I actually got this slide from Barry, who we will be talking to in a minute. And the carrier frequency is 1 kilohertz, which means that you have about 1,000 pulses per second on the blue voltage waveforms. Now, pretty much all drives allow you to adjust that carrier frequency. So the next slide is the same drive and the same load, but at 5 kilohertz. The diagram on top is at light load, almost no load. The diagram on the bottom is at full load. If we go one more slide, then we see the pulse frequency at 10 kilohertz. So the voltages never really look very sinusoidal. They look like this picket fence. It's a PWM waveform, and that's why you need a very accurate RMS meter in order to measure that, because most meters will not really measure that voltage waveform very accurately. And if you want to get even close to accurate, you really need a high-speed true RMS meter. Fortunately, we can see the voltage on the keypad of the drive, and that is very accurate. Next slide shows a 1987 vintage drive. The reason I like this picture, and I got this picture from Barry too, he had this on his bench, is because in these older drives, they didn't try so hard to squeeze everything into the smallest space possible. They didn't stack components. And so it's easy to see all the components in one picture. So you can see on the left, we have our AC to DC converter, left bottom. You have 3 blocks. They have 2 diodes each. Then we go over to the capacitors on the right, and then from the capacitors to the IGBTs. And you can see that we have 3 blocks of IGBTs. On a heat sink, you'll have 2 IGBTs or 2 switches in each block. And Barry will discuss this in more detail on the video as we actually see one. The next slide shows the same drive, but with the control board. And you can see those control boards in 1987 were huge and had a lot of components. So it's very interesting. Those control boards now are quite small. They contain very high-speed microprocessors, digital signal processors. Next slide. This slide shows the front of the enclosure, and Barry will show you this. Most drives actually don't have those push buttons and switches are, but most people are also afraid of keypads. So if all you have is a keypad on the drive, most people are going to be afraid to touch it and not know what to do with it. And I am sympathetic to that because I am afraid of keypads. I'm not afraid of this one, but if I see a keypad I've never seen before, I am really not wanting to touch that thing. So we give you lights. You can see the light on the left says power on. And so when that's on, the power's on. When it's off, the power's off. And I think pretty much anybody can understand that. We have red lights for VFD fault, VFD run, green lights for the VFD running and bypass, and they're all just clearly labeled. And then you have some switches for your handoff auto and your bypass. We got a couple more slides. Let's go to the next slide. And this shows a VFD inside of a metal enclosure. This is how I recommend that you do it. And you can see that this VFD has a number of components. I won't go over those components because Barry's going to show you them in real time. But what I want to talk about is that filter on the lower right. We highly recommend a metal enclosure with a filter on it. and we put our filters right on the outside. That's a standard pleated furnace filter, and it's pretty easy to see if it's dirty. If you have filters behind louvers, we find they tend not to get changed. But in this case, that filter's right on the outside, and it does get changed. We believe in the religion of keep the drive clean, keep it cool, and keep it dry, and it will last a long, long time. Let's go to the final slide here. And you can see a couple of different types of drives. The drives on the left are becoming much more popular. This is just a drive in a chassis on a wall. And aside from the concerns that I would have about arc flash on drives of this sort, you can see that they're cheaper and they're smaller. And so obviously cheaper and smaller is a very attractive thing. But the drive on the left really has no protection. There's no place to put other components in there. And those drives on the left we find are lasting maybe 3 to 7 years. Whereas the drive on the right, if you keep it cool, you keep it clean, you keep it dry, you change the filters, you should easily get 20 years out of a drive like that. So with that, I would like to introduce Barry Christiansen. Barry Christiansen has been with us for a long, long time. He's looks like a real young guy, but I think he has about 300 years experience. And I worked with him. He's very, very knowledgeable, and he actually repairs drives in addition to starting them up and maintaining them. So we're very, very fortunate to have Barry with us today. And with that, I will turn the time over to Barry Christiansen.
Oh, Craig, you're too kind. You've given me way too many props. But anyways, what we've done in this video, though, is we have some videos that we put together to just demonstrate kind of what we do when we get inside a cabinet, kind of how we go about, what we're doing inside the cabinet once we get there. So if you want to go ahead and start the video. All right, so the first thing we want to do is make sure when we get inside of one of these cabinets that we get the power turned off and that we verified it properly. To verify that you have all your power turned off, you need to put your proper PPE on. You need to go find your meter, which I left on the side of the door, so I had to go pick it up. And then we're going to measure our incoming voltage, and we're going to measure from A to B, B to C, C to A. Make sure that we've got 0 volts. And then also, we're going to measure from A to ground, B to ground, C to ground, and also make sure that we have a 0 volt reading. So once we've measured all that, then then you can go ahead and remove your PPE now that you have everything off. And then we can go ahead and get inside the cabinet. So the first thing I do is kind of explain what's going on inside the cabinet. We got our instrument cluster on the front, similar to like Craig showed. We have your keypad for the VFD. You got some push buttons, selector switch, and some lights. And we're going to get inside the cabinet, and the first thing that we're going to see over on the left-hand part of the cabinet, we're going to see our control power transformer. It's going to take your 480 volts down to 120. We got a 24 volt power supply, got some time delay relays, we got our ice cube relays, and then we got a terminal strip. Terminal strips for all the incoming connections. Moving across the cabinet, we got our Galt. This is a 700 horsepower VFD. Above the cabinet, we have harmonic filter capacitors. We'll talk a little more in detail about those later. To the side of the VFD, we've got our isolation cutout contactors. And what they are intended to do is turn off the capacitors when the VFD is not in use. So moving down to the bottom of the cabinet, this is our reactors. We got a line reactor, a tune reactor, part of our harmonic filter. Above that, we have our incoming main breaker. This is going to turn off power to the whole cabinet when you turn the breaker off. It also gives you protection in the cabinet. And you have some smaller breakers down on the bottom, which runs our AC units. This particular cabinet has 2 air conditioning units on it to keep it cool. So when you're looking at the breaker, you know, as we get in and check it out, you know, we always want to make sure we measure A to B, B to C, C to A to turn everything off, as well as measure it to ground as well. The reason that you do that is because if you have a switch that gets hung up sometimes, which has happened occasionally, where, you know, you might open up 2 phases but not 3 phases and then find out the other one's live. So that's the reason that we always want to measure A to B, B to C, C to A, and to ground or neutral at the same time. So now that we've verified everything's off, we kind of give you an overview of what's in the cabinet. We're going to go ahead and, you know, the first thing that we're going to do when we get inside the cabinet is we're going to just stand back and do a visual inspection. We're looking for all kinds of things inside the cabinet. We're looking for things that are burned up. We're looking for debris in the cabinet. We're looking for maybe insects have gotten inside of it, maybe a rodent. You know, we've seen all kinds of crazy things get inside these cabinets. The first thing we do is, you know, verify we don't have anything in the cabinet. Then I've proceeded to go through and I'm just kind of making sure everything's tight. Yeah, in this particular demonstration, we just did a visual pull test. A lot of times when you're checking all the connections, we recommend to use like an IR camera and do it while it's energized. You can see that using an IR camera, you can see any hot spots or any loose connections. Another way, if you don't have those available, you know, you could use a torque wrench and just verify torque that way. Now, as you're going through on these connections, you can give them a pretty good tug, especially on high power connections. You know, and if they feel like they move at all, they probably need to be retorqued. So as we move through, like I said, anything that's burnt, anything that's crispy, anything that you know, that looks to be there that doesn't belong there. All right, and we're going to open up the VFD cabinet. This one particularly has a door that opens up, makes it a little easier. Sometimes you have to remove covers to get inside the cabinet, and we do similar inspection. Make sure everything's tight. Make sure we don't have any bugs inside of it. Make sure we don't have any, you know, anything inside that's not supposed to be there. Move on up, see the control board, make sure all the control connections look normal. Yeah, make sure all the ribbon cables are intact. Just, you know, give it a quick once over. All right, then we're going to move out to the instrument cluster. We're going to go through, you notice I pushed all the buttons, moved the selector switch back and forth, verified the keypad was on tight. We want to do that. We're just making sure that the switches are, you know, when you push the button, it moves the way it's supposed to. You know, sometimes over time they get kind of bound up or freezed up. So now we're getting ready to do a capacitor test. And so what we're going to do with this is we're going to make sure the capacitors are isolated from each other. And in this case, it's done with isolation contactors. If you don't have that, you could go ahead and remove fusing if it's got fusing on, or you may have to disconnect the capacitors right at the capacitor. I'm going to get my meter out. I'm going to put my meter in capacitance, microfarad reading, which is that sign right there. I'm going to put it up in a location that I can see it as I'm measuring it. And I'm going to proceed to measure the capacitor. Now this particular capacitor, I'm measuring in the microfarads. I'm measuring about 102 microfarads. And what I'm going to do is I'm going to measure it from A to B, and you got to leave it on for just a minute because it'll charge up the capacitor as you're taking the reading. And so it'll kind of start lower and then work its way up to 102 and then kind of flatline and stay there. So you see how it hit 96, I think, when it started, and then it quickly rised up and then got to a 102 reading. That's a normal thing for a capacitor to do. And what I'm looking for is that on A to B, B to C, and C to A, they're all the same reading. If I have any kind of a very large variance, it's an indication that the capacitor has a problem. So I just got done measuring that capacitor. I'm moving to the next one. Now these two capacitors are the same size, so I should get the same reading. It's another good indicator when you're inside a cabinet with a lot of capacitors in it. You can kind of compare one from another to make sure, capacitor A is going to match up with capacitor B. And if they're all the same kVAR, they all should have a real similar reading. One thing to keep in mind is capacitors do have a little bit of a tolerance on them. A lot of them are like plus and minus 5 or 10%. If you're not right on the number, don't get too concerned. But usually if you have a bad capacitor, a measure 102 on one of them, and then the next one will be like 70 microfarads. So it'll be considerably different, or it'll be open or even shorted. So now I'm moving up to one of the bigger capacitors. Once again, we're going to do the same test, but my reading is going to be higher now because it's a larger kVAR capacitor. And on these ones, I'm getting about 175 microfarads from cap to cap. So, and one of the things I want to re-emphasize on when I'm doing this is that you always want to isolate your caps when you do this, because you could pick up weird readings from the other caps if you don't, because they're all put in the circuit in parallel with each other. So if you don't isolate the capacitors from each other, you might pick up something from one cap that you're thinking is part of the cap that you're measuring. So we've gone through and measured it. For time's sake, this is where I stop going through the capacitors, but if you're doing a test in the field, you're going to continue on and test every one of them the same, verify that they're all okay. All right, so now that we checked the capacitors out, everything looks good. I would go through at this point, measure all the fusing on it, check it out. So I'm going to measure a few of the fuses inside the cabinet. So I'm going to get over my meter set up, put my meter in ohms, and then I'm going to measure my primary of my control power transformer, my secondary of my control power transformer. Now, keep in mind, I didn't pull them out. Now, if I see a reading that looks unusual, what I'll do is I'll go and I'll pop the fuse out of the socket, and then I'll measure it isolated from everything else. Most fuses, you're going to see something that's in the neighborhood of like a 0.5 ohms or less. So if I see anything that's higher than that, you might be reading through a coil or a transformer or something like that. So I remove the fuse and just verify it. I fuse down from my 24 volt power supply. So now that I've gone through and kind of checked all the fusing out, everything's looking normal there, I'm going to go ahead and do a static check on the VFD, similar to like what Craig was showing you. So anytime you get in a cabinet, the very first thing you want to do when you're doing any kind of a static check is we're going to measure the DC bus. The DC bus can be charged for a long time, so I'm going to put my meter on DC volt. And this has been off for a while, so I shouldn't have any voltage, but I always make sure, because if you have, any more than about 7 or 8 volts, your readings are going to come back not right. So verify that all your DC bus is dead and completely discharged. Then I'm going to go ahead, I'm going to put my meter in the diode mode, which is the little blue arrow on my meter with the line in front of it. I'm going to take my positive lead, I'm going to find my negative bus and put on it. And I'm going to proceed, I'm going to measure all my inputs, which is down on the bottom. Okay, so, and I should get a reading that's going to be about the same all the way across. In this case, I had a 0.33, 0.312, and 0.32. It's pretty normal readings, all within tolerance. Then I'm going to switch my leads. I'm going to take my negative lead, put on my positive bus, do the same reading. once again, I'm getting real similar reading all the way across. It's about a 0.32. One thing to keep in mind when you do this reading, you usually are going to measure somewhere between about a 0.2 and a 0.5 on your diode rectifier or your incoming. And then on the outgoing, usually it's a little bit lower than your incoming, but it is still about the same. So it's somewhere between a 0.2 and probably a 0.4 output. Now I'm going to go ahead and measure the transistors. I'm going to take my positive lead, put on my negative bus again. I'm going to measure all my T1, T2, T3, or my UVW phases. And I had 305 all the way across on that one. I'm going to take my negative lead, put on my positive bus, and do the same measurement. And 0.310, 0.310, and 0.310 all the way across here. And so that's how you do a static check on a drive. And all drives, you're going to be able to do a similar test. So sometimes it's a little harder to find the bus. So now what we're doing is I've put my PPE back on. We've energized the cabinet, and we're going to go ahead and do our energized testing. So I measure from A to B, B to C, C to A. Should get a pretty normal reading. In our shop, I'm running about 489 or so. I'm going to measure in the front of the breaker and on the bottom of the breaker, just to verify that I don't have any losses across the breaker. And once again, I'm going to measure from phase to ground as well, make sure I have my 277 volts there. In my case, I'm about 285. And then I'm going to go ahead and measure on A phase, the top of the breaker to the bottom of the breaker. And what I'm looking for here is that I should see 0 volts. 0 volts is an indicator that all my points are good. If I measure a high resistance there, if I have a high resistance connection, I'm going to see some voltage across that. All right, so now I'm going to get in position. I'm going to measure my reactors, my line reactors, and my tune reactors. Verify that I got proper voltages moving through them. So, and in this case, your line is going to be where your line is, the same as what your incoming is. Your output of your line reactor is going to be similar to what your incoming is, maybe a little bit less. And then your tune reactor secondary bit might be just a little bit higher. So let's say you had a 480 volt system. You're going to see in the neighbor, similar to that coming out of it, out of the reactor. And then on the tune reactor, you're going to see something that's probably in the neighborhood, a few volts higher probably. So now I'm going to move over to my control power transformer. I'm going to measure my primary and my secondary of the fusing just to make sure I got all my power coming to it, as well as I got all the proper voltage coming out of it. And then since this cabinet has a power supply, I'm going to go ahead and measure the 24 volt output as well as the AC input. Make sure that I got proper voltages everywhere I should have them. Okay, I'm going to get inside the cabinet now. And I'm going to measure all my incoming voltages into the VFD again. And then once again, it's always phase to phase and phase to ground. Make sure I don't have anything that that I'm losing there. Voltages coming into the VFD should be basically what your line voltages are coming into the cabinet. If you have a harmonic filter, they may be just a little different, but they should be pretty close. Then after I've gone ahead and measured that, I'm going to move my meter to DC, and then I'm going to measure my DC bus. Now keep in mind, the DC bus is going to be between about 650 and 700 volts DC. And I'm going to measure it, make sure it all measures normally. I'm going to get my leads all tangled up. And then we're going to go ahead and take our reading. So now, like Craig was saying earlier, you can do a test where you measure an AC volts and should see 0 volts, especially while it's not running. Okay, so at this point, I'm going to get ready to do a run test so that I can measure the output of my VFD. So to do that, this particular cabinet, I move it, selector switch to the hand position, press the start button. There is a delay on this start because of our time delay relays. And once it begins to start, it's going to run up and go up to about 60 hertz. And then I'm going to measure my output. Now, you want to make sure that your frequency is stable. If you're trying to measure your voltage on the output of a drive while your frequency is moving up and down, you're going to get some readings that are going to be moving up and down, which is going to be hard to determine if you got a problem with one of your transistors gating properly. And then when you start to measure, once you have your frequency stable, which means your voltage should be stable, you're going to measure, your output terminals, and you should get a real stable voltage. And usually you're within 1 volt of each other between A to B to C phasing. If you have much more of a variance than that, then that's usually an indicator that something's not firing properly in the output. So I'll get my meter all set up again. And once again, my meter's in AC volts. And then I'm just going to measure my output terminals, which is the UVW terminals on this drive. Sometimes they are known as the T1, T2, T3 terminals. Now, when you measure this voltage, it's normal for you to measure a little high with a multimeter. For instance, this VFD is putting out about 460 volts. On my meter right now, I'm measuring something around 515 volts. And the reason my meter's picking it up that way is because of the PWM of the VFD. So don't be concerned if you're measuring something higher than what the keypad says, but what you do get concerned about is if your voltages from A to B, B to C are consistent. And once again, they need to be within about 1 volt of each other. So now I've got a clamp on meter, and I'm going to measure my capacitors. This is another test that can be done. You notice I'm getting about 18 volts on it. So your capacitors, when in operational, should have about the same voltage on all 3 phases, or same current on all 3 phases, not voltage, apologize. And you'll go ahead and measure all the capacitors that same way. And once again, the higher kVAR capacitors are going to have a higher current reading. But when you're measuring from A to B to C on it, they all should be the same on the same capacitor. All right, I want to pause. All right, so this next test that we're getting set up is a test like what Craig has showed the drive. We use this drive. We probably go ahead and get it started again. So once again, like Craig said, we like to use these older drives because when you get inside of them, you can see all the components. They're easy to see. So this is about the same vintage drive as what we've looked at before. And we're going to go ahead and we're going to pull off the control board so you can see everything inside. And then we'll go ahead and describe what's going on inside of it. So I've already removed the screws and stuff to make it a little easier to get inside. I had a few ribbon cables. I had unplugged everything. And so getting inside the drive, over on the bottom left-hand corner is your diode rectifier module. This module is going to take your AC and it's going to change it to DC. That's how it works. And then moving along, we got our pre-charge circuit, which is going to be over on the right-hand side. You can see a contactor in this case, and it's going to be in parallel with some resistors, which is more up towards the top of it. And this is designed to slow the rate of charge to the capacitors, just like we talked about earlier. And so we don't hit the capacitors with all that voltage all at the same time, which normally will cause a failure. The next piece of this drive is the DC bus capacitors, which are going to be those little blue can looking things that are sitting underneath the bus work there. And those kind of act like your reservoir. They're going to charge quickly, discharge slowly. And what the capacitors are doing in this circuit is they're just stabilizing the DC bus, taking all the ripple out of it. Then the next section is the inverter section. This is where your transistors are. This is the section that's going to take your DC and it's going to change it back to AC again to run your motor. By doing this, it can control your voltage and frequency at the same time. So just to do a recap, got your rectifier module, pre-charge circuit, capacitors, and your inverter section or your transistors. All right, now I'm going to proceed to do a diode check, similar to what we did on the other one. So I'm going to put my meter in diode mode, which is a little arrow. I'm going to take my negative lead, I'm going to put it on my positive bus, and I measure all my incoming terminals. I'm getting 465 all the way across. Once again, between 0.2 and 0.5 is a normal kind of reading. If you have anything that's open or shorted, that's a problem. Or if you get one that's way out of tolerance from the others. So let's say I had a 465, let's say one of them was measuring like 0.2, that would be a problem. All right, so now I'm going to switch my leads around. And then I'm going to measure my outgoing. So once again, negative lead, positive bus. I'm going to measure all my output. Once again, it's normal for those to measure a little bit less than your incoming, but they're all consistent with each other. So I'm getting about 375 all the way across, and that's normal. Now, if I get anything that's an open or it's a short, that's an indicator that the diodes and the transistors have an issue. Or if I get too much of a variance between the transistors or between the diodes. So now I'm doing a test that just shows it charging. And so I put my positive lead on my positive bus and I started measuring across. You notice my meter started low, then it charged up till it got to an OL. And that's what I'm looking for. If it doesn't charge up, then that's an indicator that I got to open on my DC bus somewhere. Maybe some fusing, maybe the pre-charge circuit's opened up. Something on the DC bus is not healthy. So then I do the same thing where I put my positive lead on my positive bus and I measure all my inputs and outputs again. And it just lets me know that there's a problem if I can't charge. Another way that you can, it's also an indicator that your capacitors are charging properly. If you got a bad capacitance in it, it won't charge. So that's it.
Great, thanks, Barry. We've had a few questions come in. Feel free to keep sending in questions as we go, but that is the end of the video and the presentation. So we'll just start fielding questions. This first one we'll probably send over to Barry. Someone would like a reminder on how you isolate capacitors.
So you can isolate capacitors by removing the wire or removing the connections with the other capacitors. In the case of the cabinet, we were able to, they were already isolated because they had a charge contactor in front of each one of the capacitors had its own contactor. If you're not able to do it that way, sometimes capacitors will have fusing on it. You can remove the fusing for each one. And if that's not an option, then the only way that you can do it is to just unhook the wires from the capacitors themselves to isolate. So usually one of those three methods is how we do it.
Great. We had another question come in. Let's send this one over maybe to Craig first, and then we can come back to Barry if he has anything to add. What differences are there between the enclosure that the VFD chassis has and the enclosure that houses the entire system? Are they rated differently or serve different purposes?
Yeah, they're rated the same, and I think Barry would be really good to comment on this after I do because of his experience out in the field. Typically, first of all, arc flash, which we have had seminars before, I certainly feel much more comfortable with a metal enclosure. But if we're simply talking about longevity and cleanliness of the drive, that metal enclosure has a filter on the front that filters all the air. And you go in after a year, after 5 years, you open that enclosure and it's clean. And it's got positive pressure in there, so it doesn't let any dirt come in. The fan keeps the pressure in the enclosure higher than the ambient pressure. And so they stay really, really clean. If you don't have that, you don't have the extra enclosure and the filters, then your drive is going to get dirty. And so that dirt is going to shorten the lifespan of the drive. And a lot of times the drives that don't have these metal enclosures, we tend to think of as disposable drives, because that's kind of how they're designed, and they're not meant for long life. So Barry, what do you?
No, I think you answered that very well. The only thing I'd add to that is the dirt tends to get in the heat sinks of the drive, which causes them to heat up more, which is what causes the failures. And so if you can keep the dirt out of the cabinet or out of the VFD itself, then you're going to make the longevity of your drive much, much longer. And so, like I said, we like to keep them clean and keep them cool, and if you can get those two things figured out on the drive itself, then they're going to get a lot more life out of that drive.
Great. The next question, we will start over with Barry. Do we have to test electronic parts? Some recommendations state that they might get damaged upon testing, so should we adopt a run to failure scheme?
So the test that we showed in this video, doing this, the static check is what they call that, when you're checking the diodes and transistors. Those are non-destructive tests that will not hurt your electronic components. There are other tests that you do, which is like a high pot type test that you can do. We generally don't do that on the drives themselves. We will high pot or maybe do a Mager type test on a motor component or something along those lines, to check the insulation. But the testing that we showed in this video is non-destructive testing.
Great. Also to Barry on this, if you do find that the drive is dirty, what is the proper way to clean it?
There's a lot of ways that you can clean it. Excuse me. The first one is we use compressed air a lot. We try not to use a lot of compressed air, and we blow the cabinet out with the compressed air. So like the reactors, contactors, components of that nature, we'll use compressed air. When we get inside the VFD, we got to be a little more careful. We don't want to blow compressed air across circuit boards and things of that nature. And so if you can use it to clean out the heat sink of the VFD, that would be okay to do that. You want to kind of stay away from the circuit boards with your compressed air. If your circuit boards are really dirty, then we use the canned air, similar to like what you get at a computer store. We use a canned air type solution, something like that we'll clean out the circuit boards with. So that's how we do that. And then after we've gone through and blown it all out, we vacuum it up. If there's still debris, like sometimes there's like oily kind of things on it, then we get in with a rag and just wipe everything down. We use rubbing alcohol a lot because it's a kind of a non-invasive kind of solution that cleans things up pretty well, but it's not going to destroy anything. Sometimes some of your contact cleaners and things like that, they're great on contacts, but they're really bad on electronics. And so we kind of stay away from those when we get inside to clean these type of cabinets out.
All right, we'll send this one to Craig. How often do we change out the capacitors?
On the last question, I just might mention, I agree with everything Barry says, but obviously the best way to do it is not let the drive get dirty in the first place, because once drives are dirty and full of things, it's difficult to clean them the way you'd really like. So the best way is to put the filters on, keep them clean the whole time. In terms of capacitors, generally we're finding that good capacitors in a cool room and so on should last probably 10 years. The same with the fans. Any moving parts are going to fail, and generally good high quality fans on these drives are made to last 10 years. But we would also suggests that you do periodic preventative maintenance on this. So maybe Barry can address that.
So yeah, the maintenance part of it kind of always comes down to your environment. If you're in a fairly clean room, like there's a lot of office spaces that really don't get very dirty, and you have the good filtering on your cabinet, you might only need to get inside of one of those maybe once a year. If you're, let's say, outside on like an oil rig kind of place where there's a lot of trucks and heavy equipment moving around and there's a lot of dust getting kicked up, and you put them inside one of these enclosures, it's probably good to get inside that thing maybe every 2 or 3 months, to get in, make sure your filters are not plugged, kind of wipe down all the stuff that may be dirty inside of it. And so as far as the capacitors go, like Craig said, most capacitors in the right environment are going to be in the neighborhood of 10 years. Some manufacturers recommend that you replace them after 5 years. Some recommend, somewhere between 5 and 10 years. But in our experience, most of the ones that we found, go 10 years if they're in a good environment, maybe even a little longer before they actually have a failure. But whenever we get into where we're going to do a service on it, we always refer back to the manufacturer's recommendations on some of that. So if you have a cabinet and they say you need to change the capacitors every 7 years, and that's the timeline that we're going to try to follow. So.
Great. We'll stick with you, Barry. What is the best procedure to shut down a drive safely so that you can disconnect it?
So you need to verify where all your upstream disconnects are, or breakers, or whatever it is, means of turning it off. And then you don your PPE, turn off your breaker, put a lock and a tag out on it, and then you're going to go back and open up your cabinet and verify your voltage is off.
Great. Next question, we'll start with Craig on this one. Which is best for a VFD system, floating neutral or solid earthing?
Yeah, we would generally say that you always want to have a solid earthing system whenever you can. Now, the fact is that there are places in industrial systems that use high resistance grounding, and so there's no reason you can't use that on a VFD. But if you have a solidly grounded system, we would say everything should be connected solidly to ground.
Great. Craig, we'll stick with you on this one. We looked at the internal parts of an older VFD. What changes, advancements have happened to VFDs since those VFDs, like from the 80s, were made?
Yeah, that's a really interesting question, because the basic answer is no changes. The fact is that the fully digital VFD, PWM type, was developed by the Japanese, Mitsubishi, Toshiba, Fuji, back in the late 80s. The Japanese came up with the IGBT. And if you look at a standard modern drive, the parts are going to be identical. And now, obviously, your IGBTs are better and they're faster and so on. But the basic topology of the drive, the diodes, the IGBTs, the capacitor, identical. The big changes are, number one, we push everything together. We try to make it as small as possible, and we stack components, which makes them harder to see in a video, but they're still the same components. And then the other huge change is the microprocessor and the digital circuitry. That has changed worlds. So your circuit boards are much smaller, but you have very high-speed digital signal processors. So the controls are much faster, much more complicated, much more sophisticated than they were back in 1987. But it is interesting that the topology is still the same, and we keep thinking maybe someday somebody's going to develop a brand new type of topology, but it hasn't happened yet.
As a follow-up to that question, someone asked, weren't some of those old drives SCRs?
Excuse me. Yeah, so you're asking the right guy with the gray hairs. I got into drives kind of big time in 1980, and a lot of people didn't want to use drives in 1980 because they weren't very reliable. And you're absolutely right. Back in that day and age, we had current source drives, we had voltage source 6-step drives, we had drives that were both PWM and 6-step, and manufacturers were trying a lot of different technologies back then, but they all pretty much died out other than the PWM. So yeah, you're absolutely right. Some of those old drives, particularly the current source drives, did have SCRs on the output. And if you had a standard 6-step voltage source drive, they certainly had SCRs on the input because they would vary the DC bus voltage. But that's all kind of ancient history now.
Great. Let's go back to Barry to start this one, and then we can come back to Craig. How true is the statement that some companies stop supporting their drives after 10 years?
That's actually very true. Usually what they'll do is they'll come out with a line, run it for a certain period of time, which is usually between 8 and 10 years, kind of in that neighborhood. And then after they discontinue that line where they don't make it anymore, they generally will support it for in the neighborhood of another 10 years. And every manufacturer has its own recommendations or guidelines on this. And so some drives might only support it for, maybe between 2 and 5 years after they discontinue it. Other drives, as soon as they discontinue it, they quit supporting altogether. And I've seen, all the way across the board on these. So there's really no industry standard on it, but from what we've done in the past in our history, kind of tells us in a lot of drives they're going to support the drive after it is discontinued for somewhere in the 5 to 10 year mark.
Great. Barry, a follow-up question on capacitors. Which capacitors are we talking about replacing regularly? All of them throughout the drive or just particular ones?
The electrolytic capacitors that are internal to the drive. And then as far as the harmonic filter capacitors that are in the cabinet, we generally replace those as needed, depending on their lifespan. So.
Great. Over to Craig. How do we choose a carrier frequency? Is it better to go lower or higher?
Yeah, so carrier frequencies, you have to sometimes play around with them a little bit. Most manufacturers will send out drives with a carrier frequency of about 2 kilohertz. If you get into very low frequencies, then your AC waveform to the motor is a little choppier, which actually isn't too bothersome to the motor. But the motor tends to make a lot of noise, and that that squealing, that really annoying noise that a motor makes when it's on a drive, that's very evident in the lower frequencies. So we would generally say start at about 2 kilohertz. And then if the motor is noisy, for instance, we put a bunch of motors in a hospital where we walked around the hospital at midnight. These drives and motors were on air handler systems, and we listened. We don't think that people in the hospital should have to listen to that whine of a drive. And we found out of about 42 drives, there were 3 of them where we could hear just slightly, when it was real quiet in the hospital at night, that noise coming through the air duct system. And so we ended up raising them to 3 and then to 4 kilohertz. And by the time you got to 4 kilohertz, then that noise went away. So just gradually increase it from there and until you get a noise that you can handle. If you have a filter, let's say a sine wave filter on the output that requires a certain carrier frequency, like some of them require 5 kilohertz, then you do that. You set them for whatever the sine wave filter recommends that you set them for. But generally, I'd say start at about 2 kilohertz and go up from there, but don't get crazy. Don't go way high, because the higher that carrier frequency is, the more heat you're generating in the VFD. That's going to decrease your VFD life and cause it to run hotter and decrease your VFD efficiency.
All right, Craig, we'll stick with you for this next one. If the VFD does not have braking resistors, is there a way to stop the load without allowing the drive to trip on DC bus overvoltage?
Basically, if you are trying to slow the motor down faster than it would coast to a stop, then you are going to get energy regeneration back into the VFD. Now, there are some techniques you can use in the VFDs. For instance, the VFDs can put DC current through the windings of a motor in order to bring it to a stop quicker. But for the most part, I would say either let it coast to a stop, or you're going to need those DC braking resistors. And if it's, let's say, something really small and you can bring it to a stop in a second, well, then injecting DC current into the windings is simple. And that's something that drives tend to have built into them as standard. But if we're talking about a significant load that you're trying to bring to a stop, you got to have some place for that energy to go. And so typically that's either going to have to be a regenerative drive or putting on braking resistors. And braking resistors can be added after the fact. In fact, most of them are that way. You can add them to an existing drive.
Great. That looks like all the questions we had. I want to thank Barry and Craig for both joining us and helping us learn a bit today. And we'd like to thank all of you for joining us. Hopefully you enjoyed it and learned something. And we look forward to seeing you in the future.